Okay, so at this point we've learned about finite automata, and we've learned about formal languages, and how you can recognize or generate a formal language with a finite automaton. The last part of, or actually occurs at the beginning of section 13.3, but I saved it to the end because I think it's more of a transition into the next section, 13.4. We're going to start digging a little deeper into the sort of theoretical framework behind here. We're going to look at something in section 13.4 called Kleen's theorem, which is going to introduce the notion of regular expressions, which are related to all of this. But before we get to that, we need to introduce some new operations that are based on older operations. The first two operations we're going to look at are concatenation and union. Those operations we have already defined for strings. Rather, concatenation is an operation on strings, and union is an operation on sets. So we've already defined both of those. We're just going to look at them in a new context of sets of strings. So we're combining these two notions together. Sets of strings. Let V be a vocabulary, all right? It could be like I, the input alphabet for a machine, or it could be the vocabulary that you're using for a phrase structure grammar, or just the vocabulary that you're using for a language of any type. And then we're going to have A and B be subsets of V star, not elements. So A and B aren't strings, they're sets of strings. Okay, so V star is kind of like the universal set in this context. It represents the set of all possible strings, and A and B are subsets of that. And then we're going to define each of these things, and I'm going to go through an example to illustrate them over here. So first of all, concatenation. We know what it means to concatenate two strings together, right? You just take one string, and then you put the other string at the end, smush them together to make a longer string, right? That's easy. But if you have two sets of strings, this is kind of like it's kind of like a Cartesian product where you're going to take elements of A and pair them with elements of B, and take every possible pairing. Except instead of just putting them into an ordered pair, we're going to concatenate those elements because they are strings. So we'll define this as the set of all xy, of all strings xy, where x and y are strings as well. X is an element of A, and y is an element of B. So we're taking the string x from A and the string y from B and concatenating them together. And every possible resulting concatenation we could get from that is going to be in this set called AB. So in the example over here, I have A as I have my vocabulary is 0 and 1, so I'm dealing with bit strings. A is 0 and 0, 1. Those are the two elements in A. And then B is 1 and 1, 0. Those are the two elements in B. There's my two sets. And so AB is going to be the set of all strings I can get by concatenating something from A with something from B. And I'm going to pair them together in sort of a FOIL-like strategy. So I'm going to do 0 paired with 1. And it has to be in that order because this is AB and not BA. All right? This is not a commutative operation because if you swap the order of the concatenation, you get, like this, you get different strings. So I've got 0, 1, and then I could do 0 with 1, 0. So I'll do 0, 1, 0. But then I could do 0, 1 followed by 1. So I'll take the second element of A and the first element of B. And then I'll do 0, 1 followed by 1, 0, like that. So that's the set AB. Now the fact that it shares an element in common with A is purely coincidence, right? The fact that 0, 1 is in both of these is purely coincidence. It's just because it happens to be possible to take 0 from A and 1 from B and concatenate them to get, by chance, the same element that's in A. Right? So don't take that to mean that we're taking any individual elements from sets. We're not. It always has to be one from each combined together. And as you can see, since there's two elements in A and two elements in B, 2 times 2 is 4. We have 4 elements in AB, just like a Cartesian product. And also similar to Cartesian products, you can take the concatenation of a set of strings with itself, and that you can represent that by a power. So we're going to define like a to the power n by concatenating A with itself n times. So like in this example, A squared, I'll just do the example first and I'll go back and write the definition because the definition's a little hard. The example would be elements of A concatenated with other elements of A. So we could get, for example, 0, 0, which is the first one with the first one. We could do the first with the second and get 0, 0, 1. We could do the second followed by the first, 0, 1, 0, or the second concatenated with itself, 0, 1, 0, 1. And those are all the options. So that's what A squared would be. You could then do tack on another element of A on the end of each of these and do all those possible strings and get A cubed, and so on. The way that this power of A is defined is actually recursive. We say AN is going to be defined as A concatenated with AN minus 1. But that recursive definition requires a base case. This is the recursion rule. The base case would be A to the 0. You might say A to the 1 should be the base case, but actually A to the 0 needs to be the base case in order for us to say what that is. Now, what is A to the 0? Gosh, you should pause the video. You should definitely pause the video and think about what A to the 0 should be. I'll give you some options. One possibility is that it's the empty set. Another possibility is that it's the empty string, except since A is a set of strings, and the result of this concatenation operation should still be a set of strings, lambda by itself doesn't really make sense because that's a string, not a set of strings. So two possibilities here are the empty string or the set, not lambda, but the set containing lambda, right? Like that. One of these is right. So the one that's correct is the set containing lambda. Because what we essentially want here is we want A to the 0 to be like an identity element under the concatenation operation. Normally, if you take a number and raise it to the power 0, you get 1, right? Because 1 is what you multiply by if you don't want to do anything. It's the identity, it's a multiplicative identity element in algebra of real numbers. In this case, concatenating something with lambda doesn't do anything, right? Lambda is our identity element for concatenation. So if we have a set containing lambda, if we concatenate another set with that, then that's going to be taking all of the elements from B or whatever, or another copy of A, and concatenating them all with lambda, which doesn't do anything, and it just gives you back exactly what the same set you started with. So that's what we want. The empty set, on the other hand, if you're going to take every element of A and concatenate it with the empty set doesn't have any elements to pick from, so that's more like multiplying by 0, because it would produce you would say there's nothing that you can even do. There's nothing from the second set that you can pick. And so you'd end up just concatenating with nothing and getting nothing. So we don't want the empty set. Concatenating with the empty set is like multiplying by 0. It just gives you the empty set. But concatenating with the set containing lambda is like multiplying by 1. It gives you whatever you started with. So there's our recursive definition for powers of A, which is a type of concatenation, and we're going to use that down here in a minute. The union is exactly what you expect. If you're taking two unions of sets of strings, we define that exactly like we always have, to say it's the set of all strings X that are either in A or they're in B. That's an or. Let me make that nice and big and clear. Or. So for these, A union B is 0, 0, 1, 1, and 1, 0. You add the number of elements in each set together to get the total number of elements here. Although if there's any overlap, you would omit that. So that's a maximum up to cardinality of A plus cardinality of B. So that's exactly as it always has been. And then the other totally new operation we've never seen before is what's called clean closure. We've sort of seen clean closure before in the case of a set of characters, but we haven't really seen it for a set of strings. It is the star operation that we've been using to denote the set of all strings over a vocabulary. The star operation can be applied to a set of not just characters, but a set of strings of characters, and is defined as a union, a big union, where of powers of A. So it's a union of A to the K, where K starts at 0, meaning the very first set is going to be the set containing the empty string lambda, and then we go all the way to infinity. So essentially this is A to the 0, union A to the 1, union A squared, union ... forever, which means it's going to be an infinite set. We could describe this as the set of all possible finite concatenations of elements of A. So we're talking about strings of strings, essentially. The clean closure is the set of all strings of strings from elements of A. Okay, so we're taking strings of A and then we're stringing them together and concatenating them and making bigger strings. Okay, and it's the set of all possible things of any, like with any possible number of elements from A, as long as it's a finite number of elements of A. So in our example over here, I'm gonna use set A for this, although you could do it with B as well if you wanted. The clean closure of A star, well, first of all, I'll write it out like I did here with it's A to the power 0, union A to the power 1, union A squared, union, etc., forever. So we're going to have A to the 0, which is set containing lambda, union with A itself, 0 and 0, 1, union with A squared, which we figured out earlier, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 0, 1, and then union, etc., forever, greater powers of A. So this produces a single set with all of these elements in it. And there we go. That's the clean closure. It's a bit of a complicated idea, but just make sure that you're thinking of it as taking the strings in A and looking at all possible ways of concatenating strings from A with each other, as long as you're taking a finite number of them. It's really notable that even though like your vocabulary, or even though the set you're doing the clean closure of might be a finite set, and even though every single string that results in this set is a finite string, it's still an infinite set, because the finite strings can be arbitrarily long, which occurs because this goes all the way to infinity, right? You never actually get infinite strings in this set. You just get infinitely many finite length strings of arbitrarily long length. So I hope that makes sense. Let me know if you have any questions. That's it for 13.3. We're going to use these operations in 13.4 when we look at Kleen's theorem.